with Stefan about reactive power support adequacy at the DSO and TSO interface. The floor is yours.
Thank you very much. Okay, you see my screen?
Yes, you can go on.
So thank you very much, Mr. Chairman. My name is Stefan Stankovic. I'm coming from KTH Royal Institute of Technology, Sweden. And today I'm going to present our work on reactive power support adequacy at the DSO interface. This work was done in the collaboration with TU Dortmund. To start, I will say a little bit about what is the structure of today's presentation. So I will talk a little bit about motivation about our work, our introduced flexibility coefficients, how do we introduce these D-flex and T-flex coefficients as we call them, and why do we need the definition of DSO capability surface and TSO desirability surface. Then we are going to apply this methodology on the case studies, analyze the results, and end up with some conclusions. To start, we are experiencing in the recent past nowadays, and it's most probably in the future, we will have a continuing transition from conventional to renewable energy sources, which means that, the generation will relocate from transmission to distribution grids most likely. As a consequence, this will lead to the lack of reactive power resources in transmission grids that can then induce some voltage control problems on the transmission grid. Common solution in the literature that was provided in the last 10 years is that provision of reactive power from underlying lower voltage level grids. The question is, how do we describe this reactive power potential from these lower voltage level grids? So then again, the literature provided a number of descriptions of this potential. And I just name a few here. So capability charts of active distribution networks, flexibility ranges of active distribution networks, probabilistic capability charts of active distribution networks. But what was the limitations of all these studies is that all these studies were assuming the transmission system, when calculating this capability chart of the ranges, they were assuming that the transmission system is basically at even in equivalent. So they were not considering how will this exchange of active and reactive power, the DSO-TSO interface influence the operation of the transmission system. And this is the gap that we are trying to fill in with this paper. So in order to more accurately describe this flexibility, we introduced two coefficients, D-flex and T-flex coefficient, where the D-flex coefficient is looking and describing this flexibility from the distribution system point of view, while T-flex coefficient is describing the same flexibility from transmission system point of view. One important assumption that we make in our work is that the OLTC at the DSO-TSO interface has such an operating range that the secondary voltage and the primary voltage can have any parameter values, meaning that there is no limitations on the OLTC operating range. So as I said, we are going to introduce two coefficients, D-flex and T-flex coefficient. But before we introduce them, we have first to define the DSO capability surface and the TSO desirability surface. So we introduce the DSO capability surface with the definition 1 in the paper, and it said that the DSO capability surface is a set of points in the PQ plane representing active and reactive power values at the DSO-TSO interface for each operating state of the distribution system, satisfying distribution system constraints. Thing to be emphasized here is that those are the PQ sets that are satisfying distribution system constraints. What are those kind of charts? Those kind of charts are nothing else than, as I previously mentioned and previously described, capability charts of active distribution networks and other definitions that were present in the literature in the last 10 years. Here I give just a basic formulation of how we can find these charts. So it's basically vary the active power injection and try to find the minimum and maximum reactive power injection for each parameterized active power injection from the distributed generation in the distribution grid, subject to distribution system constraints. Something that we introduce in this paper is the TSO desirability surface, and we introduce it with the definition 2. So we say a DSO desirability surface is a set of points in the PQ plane representing values of P PCC and Q PCC pairs for which the transmission system can be operated in a secure way, satisfying transmission system constraints for one or more operating points of the transmission system. So here, expression to be emphasized is satisfying transmission system constraints. So how do we I'm sorry. Okay, so how do we find this transmission system TSO desirability surface? We can add an artificial generator on some bus of the transmission system grid, and then we vary the active power and reactive power injections of this artificial generator until we hit the operating bounds of the transmission system operator. So transmission system operator will have to adapt its operation to host this active and reactive power injection, but at one point it will not be able to adapt it anymore because it will be hitting some of its own operational constraints. When we hit these operational constraints, this PQ point is exactly defining the bound of our TSO desirability surface. Putting it in mathematics, first we can find the outmost values of active power exchange, so the minimum and maximum value of active power exchange at the specific bus, by solving the optimization problem that is represented on this slide. So we have a set of equality constraints defining the power balance equations of the grid. And then we had a set of transmission system constraints. Here it can be included, we can include a number of constraints, also the economic constraints. For example, we included in our case studies also the constraints that the transmission system losses should be less than 5%, while trying to accept this active and reactive power from the distribution network. Now, when we find the minimum and maximum active power at that particular bus that we are analyzing, then in the same manner as with the DSO capability surface, we try to find minimum and maximum value of reactive power exchange for each value of active power in between these bounds. Now, when we find the DSO and TSO surface, we calculate the flexibility coefficients quite straightforward by this expression. So d-flex is basically the area of the intersection of the DSO and TSO surface divided by the area of the DSO surface, while the T-flex coefficient is the area of the intersection between DSO and TSO surface divided by the area of TSO surface. For our case study, we used the Nordic 32 as a transmission system, and we found the TSO desirability surface as the intersection of two scenarios, 100% loading case of the Nordic 32 operating point A, and also 80% loading case of the Nordic 32 operating point A. So for the candidate buses in the Nordic 32, we assumed connection of two active distribution networks, modified IEEE 14+2 test system and integrated type 4 wind turbines. And the second distribution network was a distribution system that was consisting of 50 IEEE 69 bus radial grids with integrated type 4 wind turbines. So now we can see on this example how we calculate the d-flex and t-flex coefficient. So d-flex coefficient, for example, between the second distribution grid, denoted here with the red area, would be intersection between the DSO surface and the TSO surface divided by the whole DSO surface, while the T-flex coefficient would be the same intersection divided by the TSO surface denoted here in the dark gray. So this is the example for the bus 4043. This is how this looks like for the bus 4051. And then using the same principle, we calculated the TSO, D-flex and T-flex coefficients for the number of the buses in the Nordic system. And based on the values of these coefficients, we actually could draw some conclusions. So we can see that the central area buses have smaller TSO desirability surface and higher corresponding T-flex coefficient, meaning that these buses have a higher need for flexibility from the TSO from the DSO. The size of TSO desirability surface is correlated to how strong is certain transmission system bus. So if the TSO desirability surface is bigger, that means that that particular transmission bus is stronger. While if the TSO desirability surface is smaller, then we are talking about a very weak transmission system bus. Another thing that we saw is that the higher D-flex values mean that the flexibilities of active distribution network are better used for that particular bus. another conclusion that we made is that the deflex and T-flex coefficient closely reflect how constrained is the operation of active distribution network and transmission system with respect to their common interface. Having in mind this, we can say that the deflex more or less reflects the cost of the connection to transmission grid per unit of installed power that TSO would charge DSO. So it's basically reflecting the TSO connection costs for the distribution system, while the T-flex value is reflecting the cost of DSO's flexibility provision per unit of installed power to TSO. So how much would the distribution system operator charge the transmission system operator per provision of their flexibilities? So thank you very much. This has been all from me. I'm glad to answer your questions.
Okay, thank you, Stefan, for the presentation and being perfectly on time. I'm happy that we can recover on time. I think we have some questions from the floor. I was trying to see from Dan, from Zhao. First of all, one point was about the impact on the voltage level at DSO is going to impact the flexibility of the desirability of your TSO DSO surface. And one other question was about the joint effect of P and Q optimization together. Do you want to comment on it?
About the voltage, is that I'm trying to find this question.
The question was clearly that if you have different voltage level at DSO interface.
Aha, okay.
It's the first from them.
So basically, it will. I would assume that we can control. We have a OLTC that can be controllable. So our assumption was that this OLTC range doesn't have limitations, which means that the distribution system operator can basically control its secondary voltage to any kind of value, which then means that the PQ values supported upwards can be controlled in that way from the DSO side. And the voltage level on the primary side is basically assumed in the TSO desirability surface. So we have a constraints on each of the voltage levels in the transmission system. And that also is valid for the primary side of the DSO TSO interface transformer. And another question was on the optimization.
The other question was about basically how do you solve the optimization problem between P and Q?
Yes, so I can go to the slide exactly where I was. I guess the question was more about the TSO desirability surface here. Yeah, so as I said, actually better here to represent it here. So let's say we have a TSO desirability surface, this full line gray area. First, what I will find, I would find the outmost values of P exchange. So this point here and this point here. And then I'm going to run a sequence of optimization algorithms where I parameterize the active power exchange at the DSO TSO interface. And then for each of this value of P, I found the minimum and maximum value of Q on this area. And that's how I find the area, basically.
Okay, so it's min max. Okay.
Yes, so we first find the P min and P max, and then when we find them, then we run a sequence of optimization problems where for each value of PPCC, we find the minimum and maximum reactive power exchange at the DSO TSO interface.
Okay, one more question was about how did you model, which is the model was linear or not, the approach that you were using?
No, so the model is basically non-convex and non-linear.
Non-convex.
Basically, and it was also in the polar coordinates, and this is something to, of course, be improved and can be, again, there will be a lot of discussions about finding OPF on the non-convex problem. But the results that we got were, I would say, were reasonable. So even if we were stuck in the local optima somewhere and it is not a global optima, it didn't have any issues. I mean, the operating the states of the system were indicating that we are in a good operating point in the maximization.
We cannot enter in the discussion about the non-convex multi-optimal.
Yes, that's another problem. But of course, I mean, the point of this paper is to introduce this method of finding the deflex and deflex coefficient, but each kind of optimization problem for finding the DSO capability surface or TSO desirability surface can be reformulated with any kind of optimization problem, or let's say linear optimization problem, or convexified this optimization formulation, and so on, which was not really the main topic of this paper.
Okay, one more observation from Mario, Professor Paolone, about a paper on a similar issue. I think we can just rise and point at this point. I would say very recent, May 2020. Okay, thank you. I think we can close here and move to the last presentation. I think we are going to have thank you, Stefan. I think we are having a very good session in which we have free presentation on, let's say, OPF solution, and the last two was basically on more on planning and new proposal for capturing TSO and DSO. And now we move to the last one by Alex as well. So I think you can take the floor, Alex. And the last presentation will be about coupled transmission distribution simulation to assess distributed generation response to power system faults. So we moved a little bit outside the topic. I don't see the presenter. I cannot see any presenter here. So we were going smooth, but not very last. I thought it was Alex Virpas. Are you presenting? No.
Let me make a comment.
Yes.
Alex, this is Alex Papalexopoulos. I presented the paper. Alexis Birbas is my co-author.
Okay, sorry. They mixed together in the panelist.
Paper.
Okay.
That's true. I'm here, but I'm not presenting any more papers.
No problem. There was a mixture on the panelists and the attendees. So we are missing one presenter that was, I saw it as attendees, then escape. So I think I can ask if we have a backup solution with a video.
Yes, if the presenter is not here, if we all agree, I can play the video of his presentation, which he was supposed to do. It's all okay?
I think it is right, just to conclude.
Okay, so give me a couple seconds. I will share my screen with that video of that presentation.
Because I saw it, but then disappeared.
No, but that presentation hasn't got a video. I think the last presentation was from Rick Wallace Kenyon. Is that right? Yeah, but he's not here. on the participants. I don't know what happened, or if anyone was here to replace him. We haven't got that information. So I don't know what happened to Rick.
They can raise any hand, the attendees, just to know. Okay. This is a virtual problem, as usual. Okay. Maybe, well, I think we can stop here, I would say, because I'm not going to present a paper and without any information about it. I think it's not even fair. So I asked the other panelists to be available for more question and discussion. In any case, we can close just like a little bit before if we don't have any more question. I see some tentative from question and answer. No, Dan, thank you a lot. But I think we will go short in time if we got them. So I think I will just try to sum up this session. TSO and DSO coordination, I think it is crucial for the future. And I'm very happy that we were able in the PSCC to create this type of session. And I think there are some good points and a very difficult tentative to scale up solution, proposed solution using nodal, using other non-convex application that are critical as well. So I think we are in the right way to deal with this type of issue, and there has to be some way managed. So all the tentative are correct, I would say. And I thank all the authors if they have comment on this, and specifically Marco from RSE wanted to emphasize some problems that he has faced about the modeling. That was one of the questions that rise from the audience. And for instance, if the open source that you were using is going to be available for the SmartNet project, could be interesting to know.
There is a specific deliverable in which of the project SmartNet, you can look at it by navigating within the SmartNet website, in which there are some details related to the coded, but most of it is confidential, since it has been developed by some software companies that are partners of the project. Basically, we used Python as a coding language, and then we used as solver Cplex. We also tried different kind of solvers, but basically everything has been developed with open source, except for the code for the solver. And I also tried to answer to the question I received during the presentation. You can find my replies within the answered questions in the question and answer section. I don't know if
I saw them.
In case you didn't notice that. But I'm happy to
answer. No, thank you. I have some information from Brian that there was a problem, a family emergency, so everything is fine in any case from the last authors. I think we can close here the session. I thank you all the panel, all the authors presentation, and all the attendees.